Welcome Mechanics of Materials students. This lecture we will introduce the state of stress in shear and we'll define an average shear stress. So in our previous lecture we defined stress as force per unit area, where that area was a cross-sectional area with a surface normal that was parallel to the applied stress. Well, you can apply stress like perpendicular to the axis of a structure, which is what we had before, an axial stress. And in that case, the surface normal to that cross-section was parallel to the stress. But you can also have a situation where maybe the surface normal to the surface you care about is perpendicular to the applied stress. So when the surface normal of the surface we care about is perpendicular to our stress, we have what's called shear stress. So let's take a look at this box, for example, and let's look at the top of the box. We got an area A. So if we were to define a surface normal coming from that area, it would be sticking straight up in the z direction. So here's our surface normal. So an axial stress would be due to a force that we apply parallel to n. Something like if we applied, I don't know, a force E or P, we'll call it P. Okay, that would give us an axial stress, or what's called a normal stress, because it's normal to this due to a force normal to the surface in question. We can also apply stresses perpendicular to the surface normal or parallel to that surface. So we got a couple of choices here. We can apply a force in the x direction, or we can apply a force in the y direction. So if we apply a force F in the x direction on that top face, we can basically define a stress called shear stress that is in the, it's called tau, or shear stress Zx, meaning it's on the z face, so the face whose surface normal is in the z direction, but the force that's creating that stress is pointing in the x direction. So here's a new convention introducing shear. We got the surface it's acting on, or the surface normal to the surface it's acting on, and the direction it's pointing in. So we're on the z face, and we got a force pointing in the x direction, creates a shear Zx. Okay? The magnitude of that is the magnitude of the force F divided by the whole area of this face. So we've got another option for shear. So we can have an orthogonal second shear going at 90 degrees. So if we had a force G pointing in the y direction on the z face, we would have a tau Zy, and that would be defined in its magnitude as the magnitude of the force G divided by that same area A. So two average shears. Why is it average? Because we're taking a force and we're basically dividing it by the whole area. In reality, that shear force may not be uniform. Like it might be much bigger over here at the corner, smaller in the middle, or vice versa. We don't know. One concept that we will go over as we look at stress concentrators is something called Venon's principle, which means the further away you get from places where you can apply loads or from stress concentrators, the more uniform your stress is going to be. And generally, if you're looking at loading of say an end of a bar or the end of a face, that distance from the end at which you'll get a uniform stress, so the average is equal to the stress at any point, is equal to the largest dimension that you're looking at, so give or take. So that's an assumption we're making when we say average shear. We're assuming that basically that we don't have to deal with single points that are significantly higher, even though they might be there. So how would we use this? Anytime we're loading something sideways. So let's take that same cylinder that we had in our definition of normal stress, and rather than loading it along its axis, we're not going to do that. X. We're going to load it with force R parallel to its ends. And then we're gonna put a loop around it in the middle and yank it the other way. So it's in static equilibrium. We're not gonna let it accelerate in the R direction or the F direction, so we can say 2R equals F. And we can define from that the shear stress that is present at any one of these faces as being R over A. And if R equals F over 2, we can say that the shear stress is F divided by 2A. So if we've got a cylinder, like say my pencil, if I restrain it with 2 fingers and I pull with my middle finger, that's the situation I have. So you might test for shear strength by constraining a bar-shaped specimen at both ends, maybe having it fit into a recess and then yanking on it with some controlled force in the middle. That puts it into shear. So a practical example of shear stress, say we have an automobile and we've inflated the tires, and the tires deform a little bit. They're not rigid. So they have a pressure of, we'll call it 200 kilopascal, so that's 200 times 10 to the third newtons per square meter. We've defined the coefficient of friction tire to road as 0.6, and we say the car is skidding. So if we can define a normal force between the road and the vehicle, that normal force times the coefficient of friction tire to road is going to be the shear stress. And then if we can define how much that tire has flattened and what its contact area is, we can divide that parallel stress, frictional force, or excuse me, we can divide the frictional force, by the footprint of the tire, the flattened bit of the tire that's contacting the road, and get a shear stress. So friction force, parallel to the tire, parallel to the road, divided by the flattened area, gives us tau tire road, basically. So for that, we can first start with, okay, how much normal force is acting on each tire? Now we'll assume that the vehicle weight, which we're told is 15 kilonewtons, we'll say it's carried equally by all 4 tires. So the normal force for each that's coming up for each tire is going to be 14 kilonewtons divided by 4. So that's 3.5 kilonewtons, which means the frictional force is 3.5 kilonewtons times coefficient of friction. So we have 2.1 kilonewtons acting parallel to the ground. So that's our shear force. So shear stress is just that divided by whatever area we have. Well, we can get the area by back through the definition of normal force. So the tire pressure is 200 kilopascals. So that means there's 200 times 10 to the third newtons of force per every square meter of contact area of tire per tire. So we know we have 3.5 kilonewtons of force divided by whatever the tire to road contact area is going to have to give us that tire pressure, that 200 times 10 to the third newtons per square meter. We can almost do this kind of with a units analysis. So we have the force based on the 15 kilonewtons divided by 4, so the per tire force. So we just need the area, so we can just literally divide the force per tire by the tire pressure to get the contact area. So we can get our shear stress by dividing the frictional force by the contact area, and that'll give us our total shear stress felt at the tire to road interface on the average. It probably won't be uniform over that entire 0.0175 square meters of contact, but that'll be the average. So Why would we care? We might want to make sure that, say, the lamination of whatever kinds of reinforcers to rubber can withstand at least that much shear stress without delaminating and failing. That might be one reason we would need to know it. That would be a lower limit of shear stress, shear strength of that sort of composite tire material. So that is it for this very mini lecture on average shear stress. So to recap, force parallel to the surface, which we can have in either of two orthogonal directions, divided by the area of that surface, defines shear stress. Our typical notation for shear stress is tau, Greek letter tau, with a subscript of face normal, the direction of the normal to the face that the shear stress is operating on, and then the second letter is the direction, the XYZ or R theta Z, whatever coordinate direction that the force that is exerting that shear stress responsible for generating it is pointing. So on any one of our faces of our XYZ cube, we can have two different shear stresses orthogonal to each other. And other than that, just remember that we are applying, again, equations of equilibrium. So if we want to relate shear stress for any given loading condition, we have to translate stress to force, equate the forces, and then go back and divide by the applicable area over which it's applied. And if we're yanking at 2 points, we have 2 points at which we're applying that shear force, and so we have to equate that to our other loading. Hence we get our division by 2 there. We can have multiple different scenarios where that value will change. We just need to apply our FBDs first. Obviously, if our cross-sectional area changes, we might have the same force, but we're going to have a much higher stress if, say, this area was smaller at one end. So that's shear stress. So now we have two types of stress. Normal stress with a sigma, which is parallel to the surface normal and is generally viewed as being axial, perpendicular to a surface, and we have shear, where the force is parallel to the surface, perpendicular to the surface normal, and can go in either one of two orthogonal directions on any given surface. So next we'll dive into more generalized expressions for state of stress at a single point, and then look at relating differential equations showing expressions for stress and force. And then we'll, in the strain chapter, which will follow this one, we'll follow the same kind of pattern for strain.